Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. For now, we will discuss about multi-view orthographic projection. But before that, we have to discuss about the intro, the intro before we discuss about this topic. In technical drawing and computer graphics, a multi-view projection is a technique of illustration by which a standardized series of orthographic two-dimensional pictures are constructed to represent the form of a three-dimensional object. Up to 6 pictures of an object are produced, called primary views, with its projection plane parallel to one of the coordinate axes of the object. So if we have the cubes, so just imagine the cubes. The cubes has 6 planes in every sides. So that thing that we call about primary views. The views are positioned relative to each other according to either of two schemes, first angle or third angle projection. In each, the appearance of views may be thought of as being projected onto planes that form a six-sided box around the object. So, like I said before, So just imagine we have the cubes and we have an object inside that cubes, and then we look into the object but through the plane of the cubes. Although 6 different sides can be drawn, usually 3 views of a drawing give enough information to make a three-dimensional object. These views are known as front view, front view, top view, from the top, so we look at the object from the top, and then the end view, we look the object from the back side. Other names for these views include plane, elevation, and section. When the plane or axis, so we will discuss this later, when the plane or axis of the object depicted is not parallel to the projection plane, and where multiple sides of an object are visible in the same image, it is called an auxiliary view. And the overview, from our topics. To render each such picture, array of sides, also called a projection line, projection ray, or line of sight towards the object is chosen, which determines on the object various points of interest. For instance, the points that are visible when looking at the object along the ray of sight. Those points of interest are mapped by an orthographic projection to points on some geometric plane, called a projection plane or image plane, that is perpendicular to the ray of sight, thereby creating a 2D representation of the 3D object. So we can also say that what we discuss here, array offset or projection line or projection ray or line offset is a line that located perpendicular to the plane, to the every plane of cubes that we discussed before. Customarily, two rays of sight are chosen for each of the 3 axes of the object's coordinate system, that is, parallel to each axis. The objects may be viewed in one of two opposite directions, making for a total of 6 orthographic projections or views of the objects along a vertical axis, often the y-axis. The top and bottom views, which are known as planes, because they show the arrangement of feature on a horizontal plane. But the view is from the top, So our position is in the top of the object, and we look at the object in the bottom, such as floor in a building. Along a horizontal axis, often the z-axis, the front and back views, which are known as elevation, because they show the height of features of an object such as a building. Yeah. And then the third, along an orthogonal axis, often the x-axis, the left and right views, which are also known as elevation, following the same reasoning. So this is there is we have three primary axis, so y-axis, axis, and x-axis. The y-axis for vertical axis, and then z-axis for horizontal axis, and x-axis for orthogonal axis. These 6 planes of projection intersect each other, forming a box around the object. Yeah, this box is equal to the cube that I said before. Yeah, the most uniform construction of which is a cube. Traditionally, these 6 views are presented together by first projecting the 3D objects onto the 2D faces of a cube and then unfolding the face of the cube such that all of them are contained within the same plane, namely the plane of medium on which all the image will be presented together, such as a piece of paper or a computer monitor, etc. However, even if the faces of the box are unfolded in one standardized way, there is ambiguity as to which projection is being displayed by a particular face. The cube has 2 faces that are perpendicular to a ray of shade. The point of interest may be projected onto either one of them, a choice which has resulted in 2 predominant standards of projection. So the first is first angle projection, and then the second is third angle projection. First angle projection, in this type of projection, the object is imagined to be in the first quadrant because the observer normally looks from the right side of the quadrant to obtain the front view. The objects will come in between the observer and the plane of projection. Yeah, just imagine that. Therefore, in this case, the object is imagined to be transparent, and the projectors are imagined to be extended from various points of the object to meet the projection plane. When these meeting points are joined in order on the plane, they form an image. Thus, in a first angle projection, any view is so placed that it represents the sides of the objects away from it. First angle projection is often used through parts of Europe, so that it is often called European projection. So first angle projection, we can also call it as an European projection. And then the second is about third angle projection. In this type of projection, the object is imagined to be in the third quadrant, again, as the observer is normally supposed to look from the right side of the quadrant to obtain the front view. In this method, the projection plane comes in between the observer and the object. So I hope you can get the differences from this sentence and this sentence. Therefore, the plane of projection is assumed to be transparent. The intersection of this plane with the projectors from all the points of the object would form an image on the transparent plane. Multi-view projection shows the primary views of an object, each viewed in a direction parallel to one of the main coordinate axes. These primary views are called planes and elevation. Sometimes they are shown as if the object has been cut across or sectioned to expose the interior. These views are called X-section. So this is what is a tree diagram, yeah, about so this is like a tree diagram about the distribution of the classification about projection, yeah, graphical projection. So here, what we discussed in the previous section is described here about first angle and then third angle. Okay, so the first we will talk about plan. Yeah, this is a example of plan image of the house. So we have a dining room here, eating kitchen here, laundry here, entrance here, family room here, etc. So plan is like a pictorial view that as if our position is in the top of the object. A plane, yeah. A plane is a view of a three-dimensional object seen from vertical above. It may be drawn in the position of a horizontal plane passing through, above, or below the object. The outline of a shape in this view is sometimes called its plane form, for example, with aircraft wings. The plan view from above a building is called its roof plane. A section seen in a horizontal plane through the walls and showing the floor beneath is called a floor plan. So this is a floor plan. If we have a building, we cut we make a section in the middle of the wall, yeah. So we can look at the interior of this building. If we have a building and our position in the top of building and um, we look at the bottom, we just look at the roof plan. But if we want to look at the interior of this building, we have to make a section plan horizontally in the middle of wall. So we will have a floor plan like this picture. And then the second thing is elevation. Elevation is the view of three-dimensional objects from the position of a vertical plane beside an object. In other words, an elevation is a side view as viewed from the front, back, left, or right, and referred to as a front elevation, left or right side elevation, and a rear elevation or a back elevation. An elevation is a common method of depicting the external configuration and detailing of a three-dimensional object in two-dimension. Building facades are shown as elevation in architectural drawings and technical drawings. Elevations are the most common orthographic projection for conveying the appearance of a building from the exterior. Perspectives are also commonly used for this purpose. A building elevation is typically labeled in relation to the compass direction it faces. The direction from which a person views it, the north elevation of a building, is the side that most closely faces true north on the compass. Interior elevation are used to show details such as millwork and trim configuration. In the building industry, elevation are non-perspective views of the structure. These are drawn to scale so that measurement can be taken for any aspect necessary. Drawing sets include front, rear, and both side elevation. The elevation specify the composition of the different facets of the building, including ridge height, the positioning of the final fall of the land, exterior finish, roof pitch, and other architectural details. A developed elevation. A developed elevation is a variant of a regular elevation. Uh, is a variant of a regular elevation view in which several adjacent non-parallel sides may be shown together as if they have been unfolded. For example, the north and west views may be shown side by side, sharing an edge, even though this does not represent a proper orthographic projection. And then the third thing, yeah, we have a section. The section picture is like here, yeah. For example, this is about nut, bolt, yeah. A section or cross-section is a view of a three-dimensional object from the position of a plane through the object. A section is a common method of depicting the internal arrangement of a three-dimensional object in two dimensions. It is often used in technical drawings and is traditionally cross-hatched. The style of cross-hatching often indicates the type of material the section passes through. With computed axial tomography, computers construct cross-section from X-ray data. Then auxiliary views that I showed before, yeah. An auxiliary view or pictorial is an orthographic view that is projected into any plane other than one of the six primary views. These views are typically used when an object has a surface in an oblique plane. By projecting into a plane parallel with the oblique surface, the true size and shape of the surface are shown. Auxiliary views are often drawn using isometric projection. So, what is it an oblique plane? What is it an oblique surface? What is it an isometric projection? This term here, what we call it as oblique plane or parallel projection or isometric projection, it is like we look an object but in a 3D view. So if we look the cube from the front, we have just a rectangle. But if we look a cube for one corner, yeah, so our point of view is the one of the corner of the cube. So we will have um, three sides, yeah, not just a rectangle, but we will have three sides of the cube. So oblique projection or isometric projection or perspective projection is just like we look at the 3D object but in the way of 3D projection. Okay, what is multi-views? Yeah, modern orthographic projection is derived from Gaspard Monge's Descriptive Geometry. Monge defined as a reference system of two viewing planes, horizontal H or ground and vertical V, backdrop, yeah, here. So we have a V plane and H plane for horizontal and V plane for vertical plane. These two planes intersect to partition 3D space into four quadrants, yeah, which he labeled quadrant 1 above H in front of V here, and then quadrant 2 above H behind V, quadrant 3 below H behind V, and quadrant 4 below H in front of V. These quadrants labels are the same as used in 2D planar geometry as seen from infinitely far to the left, taking H and V to be the x-axis and y-axis respectively. The 3D objects of interest is then placed into either quadrant 1 or 3 equivalently. The position of the intersection line between the two planes is shifted obtaining first and third angle projection respectively. Quadrant 2 and 4 are also mathematically valid, but their use would result in one view true and the other view flipped by 180 degrees through its vertical center line, which is too confusing for technical drawings. In case where such a view is useful, like a sailing viewed from above, a reflected view is used, which is a mirror image of the true orthographic views. Wong's original formulation used two planes only and obtains the top and front views only. The addition of a third plane to show a side view, either left or right, is a modern extension. The terminology of quadrant is a mild anachronism. Anachronism is as a modern orthographic projection with three views correspond more precisely to an octant of 3D space. And then in the first angle projection, the object is conceptually located in quadrant 1. So in here, quadrant 1. It floats above and before the viewing planes. The planes are opaque, and each view is pushed through the object onto the plane furthest from it. Extending to the 6 sides box, each view of the object is projected in the direction sense of sight of the objects onto the opaque interior walls of the box. That is, each view of the object is drawn on the opposite side of the box. A two-dimensional representation of the object is then created by unfolding the box to view all of the interior walls. This produces two planes and four elevations. So, two planes is planes from the top and from the bottom, for elevation from the front and back side, and then the left and right side. So we have two planes and four elevation. A simpler way to visualize this is to place the object on the top of an upside down pole. Sliding the object down the right edge of the pole reveals the right side view. So this is what we discussed before, an image of an object in a box, in a box. The same image with views of the objects projected in the direction of sides on the walls using first angle projection. So we have this view if our position here and look at the object. We have this view if our position is in the bottom of the object. We have this view if we stand in the back of the object. And then similar image showing the box unfolding from around the object. If we from the top we look the object like this. If we from the bottom we look the object like this. If we from the front, we look the object like this. If we stand in the side, we look the object like this and this. So the cube, we unfold the cube to be like this. Image showing orthographic views located relative to each other in according with first angle projection. In the third angle projection, the object is conceptually located in quadrant 3. Its position below and behind the viewing planes, the planes are transparent, and each view is put onto the plane close to it. Using the 6 sides viewing box, each view of the object is projected opposite to the direction of sides onto the exterior walls of the box. That is, each view of the object is drawn on the same side of the box. The box is then unfolded to view all of its exterior walls. A simpler way to visualize this is to place the object in the bottom of a ball. Sliding the object up the right edge of the ball reveals the right side view. Here is the construction of third-angle projection of the same object as above. Note that the individual views are the same, just arranged differently. So we have the object here, like we have before, but okay, the third angle projection is projection that I think this is very familiar to our eyes, yeah, because we draw view from here in this side. We draw the view from here in this side. We draw the view from top is in here in this side. So third angle projection is like projections with simple ways. Yeah. I hope you will I hope you can find a difference from this projection for the third angle projection and the first angle projection. Both of these images produced from the same object, yeah. But the first angle projection result this projection, and the third angle projection result this projection. Okay, and then we will talk about symbols. Yeah, great deals of confusion has ensued in drafting rooms and engineering departments when drawings are transferred from one convention to another. An engineering drawing, the projection is denoted by an international symbols represent a truncate cone in either first angle or third angle projection, as shown here. Yeah. The third interpretation is a solid truncated cone with the small end pointing toward the view. The front view is therefore two concentric circles. The fact that the inner circle is drawn with a solid line instead of dashed in the identifies these views as the front view, not the rear view. The side view is an isosceles trapezoid. In first angle projection, the front view is pushed back to the rear wall, and the right side view is pushed to the left wall. So the first angle symbol shows the trapezoid with its shortest sides away from the circles. In that angle projection, the front view is pulled forward to the front wall, and the right side view is pulled to the right wall. So the third angle symbol shows the trapezoid with its shortest side towards the circles. Yeah. Okay, so this is for third angle projection, and this for first angle projection. Okay, multi-views without rotation. Orthographic multi-view projection is derived from the principle of descriptive geometry and may produce an image of a specified imaginary object as viewed from any direction of space. Orthographic projection is distinguished by parallel projectors emanating from all points of the image object and which intersect of projection at right angles. Above, a technique is described that obtain varying views by projecting image after the object is rotated to the desired position. Descriptive geometry customarily relies on obtaining various views by imagining an object to be stationary and changing the direction of projections or viewing in order to obtain the desired view. Using the rotation technique above, note that no orthographic view is available looking perpendicularly at any of the inclined surface. Suppose a technician desires such a view to see. Look through a hole to be drilled perpendicularly to the surface. Such a view might be desired for calculating clearance or for dimensional purpose. To obtain this view without multiple rotation requires the principle of descriptive geometry. The steps below describes the use of these principles in third-angle projection. So figure 1 here shows pictorial of the imaginary object that the technician wishes to image. Yeah. Another figure 2. The object is imagined behind a vertical plane of projection. The angle corner of the plane of projection is addressed later. And figure 3. Projectors emanate parallel from all points of the objects perpendicular to the plane of projection. Figure 4. An image is created thereby. Figure 5. A second. A horizontal plane of projection is added perpendicular to the first. Yeah. Then figure 6, projectors emanate parallel from all points of the objects perpendicular to the second plane of projection. Yeah. Figure 7, an image is created thereby. Figure 8, the third plane of projection is added here, perpendicular to the previous two. Figure 9. Projectors emanate parallel from all points of the objects perpendicular to the third plane of projections. And then figure 10, an image is created thereby here. And then figure 11, the fourth plane of projection here is added parallel to the chosen inclined surface and inclined surface here, and perforce perpendicular to the first frontal plane of projection. And then figure 12, projectors emanate parallel from all points of the objects perpendicularly from the inclined surface and perforce perpendicularly to the fourth auxiliary plane of projection. Figure 13, an image is created thereby. Figure 14 until 16 here, the various planes of projection are unfolded to be planar with frontal plane of projection. Yeah, here we rotate here, and then here we rotate here. We have this picture, we rotate here. And then the final figure, figure 17, the final appearance of an orthographic multi-view projection, and which includes multi-view projection, and which includes an auxiliary view showing the true shapes of an inclined surface. Okay, thank you for this session.